world where we space threats faster, monitor deep space events in real time, and enhance global security, all using satellites that are already orbiting Earth. This isn't science fiction, it's a real possibility through the addition of space face-facing cameras on the Starlink satellite network. And best of all, this is completely feasible with today's technology and based on sound, well understood science. Currently, our primary method for detecting near Earth objects, or NEOs, relies on a mix of ground based telescopes and a few specialized space observatories. Facilities like Pan-STARRS in Hawaii, the Catalina Sky Survey in Arizona, ATLAS in both hemispheres, and the orbiting NEOWISE Observatory have made substantial contributions to planetary defense. However, they all share critical limitations that leave large portions of the sky under-monitored or temporarily blind. Ground observatories are bound by daylight cycles and weather conditions, preventing full-time coverage and introducing unavoidable gaps in data. Clouds, rain, snow, and even atmospheric turbulence can blur or block observations. Most crucially, objects that approach from the direction of the sun, a blind spot for Earth-based telescopes, are difficult or impossible to detect in time. Several surprise events in the past have made this vulnerability clear. Each observatory can only scan a portion of the sky at a time, and even with coordination, their field of view is limited by the curvature of Earth and local terrain. Earth's rotation further restricts when and where observations can be made, leading to a disjointed global monitoring network. On top of that, communication delays and limited data processing capabilities can create time lags between an object's detection and a public alert. Now imagine a better approach, one that leverages what we already have in orbit. The Starlink satellite constellation, designed to provide global internet coverage, consists of thousands of satellites in low Earth orbit, arranged in a dense and redundant mesh. By equipping these satellites with outward-facing cameras, we can transform this communication network into a real-time, all-sky observatory. These satellites orbit above the atmosphere, free from weather and daylight constraints, allowing continuous monitoring of space in all directions, including the sun-facing side that ground systems can't see. Since the satellites are distributed globally, they can monitor the entire sky at once, a feat impossible from the ground. With overlapping fields of view and a high refresh rate, this network could detect and track fast-moving objects with unprecedented coverage and precision. Using multiple satellites to view the same object from different angles enables rapid triangulation of position and trajectory. This geometric method, grounded in classical physics and orbital mechanics, allows for fast, accurate estimations of an object's size, speed, and path, key data for assessing risk. Starlink's infrastructure includes high-speed optical laser links between satellites and fast downlinks to ground stations. This makes real-time or near real-time data transmission not only possible, but efficient. The moment a potential threat is identified, alerts can be sent across the globe in seconds, not hours. This kind of responsiveness could be critical in the event of a high-speed incoming object or sudden space weather anomaly, and the benefits go far beyond planetary defense. These space-facing cameras could play a vital role in tracking orbital debris, an increasingly serious problem as space becomes more congested. With many satellites capturing multi-angle views of fast-moving debris, we could map their paths and predict collisions well in advance, giving time to maneuver spacecraft or mitigate damage. This would enhance safety for all space assets, including those from other countries and companies. Moreover, these cameras could provide constant monitoring of solar activity, such as solar flares and coronal mass ejections, which can disrupt communications, power grids, and navigation systems on Earth. Being in the perfect position to monitor the sun from multiple angles, this system would give scientists earlier warnings and more accurate models for forecasting space weather. Another potential use is simulating a synthetic aperture telescope. By combining data from multiple satellites as they move through orbit, we can effectively create an extremely large virtual telescope. This technique would enable high-resolution deep space imaging far beyond what a single small satellite camera could offer. Such a system could help discover and study distant galaxies, track transient cosmic events like gamma ray bursts, and even support the search for exoplanets by